I want to do a quick introduction. Just like we did yesterday, I'm not going to read out the full bio. You can read it on the website because all of our speakers are very distinguished and we don't want to take 5 minutes of their time speaking of their accomplishments. So I'll keep it brief. So Michael Mahoney is at the University of California at Berkeley, where he's on the faculty of the Department of Statistics and the International Computer Science Institute. He's also an Amazon scholar and a research scientist at Lawrence Berkeley National Lab, and he's very confused about how much time he spends in each location. But other than that, he does very many interesting things, and we're very happy to have him.
All right, well, thanks for the maybe very realistic intro. Not only am I confused about that, I'm actually confused about what foundation models are. So I didn't tell you this, but I don't actually know what I'm talking about. So I do know what different people say foundation models are. So maybe I'll start with that and just share some general thoughts. But it's sort of, to my mind, it's a good chance because it's hard to get much done unless there's some sort of disaster going on that changes the landscape of how different areas view problems. And this is a great thing because I think everyone's viewing this in sort of different ways. And so if you want to move forward foundations of data, if you want to move forward machine learning or scientific machine learning or science, whatever you want, this is a good sort of way that things may get shaken up. So let's see. That's not going to advance it, I think. So what are sort of, take a step back, and success drivers for a lot of the work in machine learning? And machine learning is much broader than neural networks. Machine learning is sort of a clannish area, and they glom onto things. There's boosting, and there's kernels, and neural networks, and language models. So, but ask what's responsible for a lot of the developments in recent years? And a lot of data. 20 years ago, there was a lot of data, and now we poo-poo that. So a lot of data is relative to the time and the compute you have, but a lot of data. When it gets standardized into benchmarks, then the community can glom onto it and build things around it. A lot of developments in theory. So by theory, the word theory is used, I've thought a lot about foundations of data. The word theory is used in very different ways in science than in applied math and theory of computing and statistics. And so this is a loaded word, but in particular in stochastic optimization theory. There's a relatively strong theory practice gap, but to just stipulate that. But a lot of work on stochastic optimization, a range of things. I actually came to it from a couple different directions, but one of which is a lot of work on sort of randomized linear algebra. So stochastic optimization, a lot of work on hardware, in particular GPUs, but a lot of other things, right? So I have a figure here just for eye candy. I don't actually particularly like this figure. You can argue about the taxonomy. Should it be this? Should it be that? And everyone has an opinion. But a lot of data and theory and hardware developments. What you don't see here is anything about the science. And so we're going to talk about physics here, broadly defined. But how does your natural language understanding enter into NLP models? Or how does your understanding of pictures enter into computer vision, right? It's a heavily engineered area, but how does it enter? And it often enters very indirectly. You rotate images, you do a range of other things. You have a range of tasks, sentiment analysis. You read a paragraph, and what does that mean, right? I mean, what's the sentiment of a paragraph? And so I like, in particular, since a lot of people here are probably thinking about computation and computational science and various sorts of science and engineering, Tinsley Oden has a nice quote that says, the angle's here a little bit tricky. I was assuming I could read it. So computational science, you should think of this, it didn't exist forever, right? It didn't exist till 1950, right? And so you had theory, which you'd do with pencil and paper. You had experiment or observation, you'd go out and look at the world, and then there was a big crisis. What do you do with the computer? I mean, it might help you go beyond inverting 4x4 matrices to do 10x10 matrices, right? So there's a huge opportunity to do 10 or 11x11 matrices, right? And so now, 70 years later, you see that it's had a lot bigger effect on society than just that. And so in particular in computational science, it allows you to analyze past events and look into the future. And this is important because the sort of underlying metaphysics of a lot of machine learning is there's a bunch of data. There's a bunch of data, there's nothing else. You're just learning functions, you parameterize it however, you swap in parameterizations depending on what you like. And the way these models are validated is nothing but evaluation on test data. Of course, training and test data are a little bit different. You might want to go out of domain to tomorrow's data, which is going to be different. Whereas in science, you want to say that the things the data is a means to an end. It's a means to understanding something about the world. So you really want to say something about the underlying model. So there's a big disconnect there, and in particular, it allows you to look into the future. I mean, people do simulations to make very precise predictions about the future. And so how do you do that? So what people want to do in scientific machine learning is cook science in And in the same way as I think in the creation of scientific computing, you had this clash between continuous mathematics and functional analysis and making it discrete and putting it on a computer. And that was not an easy birth. You had numerical analysis and backward stability and conditioning and so on. You're seeing a similar thing. Two very different worldviews that approach problems in different ways, and there's a real clash. And so you can get a lot of hello world results, and so we're seeing that in the community now. And how do you build out the foundations of that? That's what I want to talk a little bit about. And so if you're familiar with computational science, maybe the best analogy is if you know what the Euler method is. An Euler method is something you see on page 1 of a numerical analysis book. It's a wonderful toy little thing. You have a smooth function. You discretize it, and you say, well, look at the smooth thing. Looks about the same. Everything after that, you say, don't use that because it's bad. It's not stable. You need better precision. You need midpoint. You need RK4. So we're sort of there, right? So you see a bunch of examples of this hello worlds. You have something, the ML analog of the Euler method, cooking science in. And so, it breaks. It has problems. And so we want to build out that foundation. So I think to deliver on the promise of this, you really need that sort of infrastructure. All right, so what's a foundation model? I told you I don't know. And then walk through a couple other questions. So, okay, so informally it's sort of a model that can be trained, can be applied to a range of things. So the term was coined in a Stanford report. Who's read the Stanford report? Okay, who's read the whole Stanford report? All right, good. So at least read the intro. It's 200 pages. The report's 200 pages. The intro is 10 pages, whatever. So don't go home and offer any opinion on foundation models until you've read the report, right? You might agree, you might disagree, but at least have an informed opinion if you take nothing else from what I'm talking about here. All right, so what they said is a foundation model is something that's trained on a broad range of data, generally with self-supervision at scale, and can be adapted, fine-tuned, to a range of downstream tasks. So it's going to be trained and then adapted. Trained, there's going to be some scaling issues, and adapted fine-tuning issues. These will be some of the core foundational questions, how to do that properly. So Joe Biden weighed in and said it needs to be trained. It uses self-supervision. He's very prescriptive. It needs to have 10 billion parameters, and it's applicable across lots of things. Down the street, the U.S. House disagreed. The House is under the control of the Republicans, Democrats, so they got to negotiate. It's not all worked out. So they say it's 1 billion parameters. It exhibits, could easily be modified. So the title of the Stanford report is On the Risks and Opportunities of Foundation Models. I hope maybe part of the negotiation is Biden will say there's opportunities and they'll say there's risks and they'll come to a negotiation because the U.S. House, and this is admittedly is not the full U.S. House because they can't elect a speaker. This is in some subcommittee report, I think, and so on. So don't take it as definitive. But they carved out a very defensive stand and said exhibits, tasks could pose a serious risk, right? So it's foundation models are bad things. They could pose serious risks. So there's risks and there's opportunities. There's risks in the computer when you do numerical computation. There's opportunities. There's risks here. There's opportunities. So what can we do here? All right. So in a little bit more detail, what you should think of these things is you walked here on the street and the sidewalk, right? You came on the side. You didn't cut across the quad, I hope. He flew in. Okay. So you took advantage of the fact there's an airport to land in. I mean that's transportation infrastructure. You have an iPhone that you use to navigate your plane, that's infrastructure, right? Your iPhone took advantage of an IEEE floating point standard. That's infrastructure. This is just a foundation on which you build things. So it's a general purpose technology on which you can build things. It's built using well-established techniques. It's in some sense a new paradigm in the way you think about data, because data is usually something you jam into an algorithm, and here it's really something you scale, model, and data and compute. So it's a very different way to think about theory, but it's reusable infrastructure. And so you want to build stuff, right? It's expensive to build, the same way roads and airports are expensive to build, but you can adapt it to anything you want. And so you can land on the quad if you want, and it's nice and flat. So you can use it. So really, you should think of it as a foundation for things. And the report was very explicit about this. It said, we could call it a large language model, but that's very prescriptive and narrow because the modalities could be much more than text. It could be self-supervised, but that's a particular technical thing that ML people do to get there. It could be a pre-trained model that really emphasizes the disconnect between what you did and emphasizing the post-training. It could be a foundational model, but there's nothing foundational in terms of foundational principles that you necessarily reveal. It's a black box thing, and so the internals of the model are not validated via some sort of counterfactual or any falsifiable thing. So the name was intended to emphasize the function, the function that can be used to a wide range of things. So now in computational science, because there's a particular infrastructure in compute, you can do things at scale with compute that are better than experiments. as a base. So question, can you do that going forward with something like this? So there's a bunch of examples of language models, but more recently a range of other modalities in science area A and B and C. So the general question, or a first question, is can we hope to adapt these sort of ideas to something for science? Defined however. So we've seen a bunch of examples of that. So what does that mean? How would you incorporate physical knowledge, and is it easy, is it hard, does it break? And so I wanted to walk through some examples of things we've done, and what are some foundational questions that will arise that, that I think are under the hood in a lot of where you see some successes and where you see, well, oftentimes you don't see the non-successes because they don't get reported, but where you see some non-successes. And then depending on time, I'll talk about some of these other things. All right, so what are you going to do here? So one thing I think people, when they first saw this, is just call ChatGPT, maybe with some fine-tuning, and get a prompt so that you can say, what comes after the top quark, or where do I find a new drug or something. So that'll happen, and people are doing things like that. They'll take an existing publicly available model, they'll ask questions, and they'll do various things, maybe fine-tuned on data from some domain. A different use of existing language models is to say, these things have remarkable stuff built into them. We don't quite know it. Can I use it as an embedding for other things? So in the same way as you use spherical harmonics, because they're nice basis functions for pencil and paper, and it can remove lots of computation if you integrate out quadratic terms from Gaussian integrals and only deal with, cook in certain things in terms of the basis functions and use them. It's not obvious, but you can take a language model. You can, Chronos is something I'll point to later with Amazon people, and you can use that to predict time series for a wide range of tasks comparable with state-of-the-art benchmarks out there. You can take that in a much more sophisticated way and beat non-public benchmarks. And you can imagine time series forecasting is important for financial companies and Walmarts and Amazons and things of the world, as well as extreme weather forecasting. So in a non-black box way, but with a couple weeks of good engineers' time, so not a huge lift, you can match state-of-the-art. So that'll happen. That'll continue to happen. What I want to talk about today is something a little bit different, where you say, I really want to understand the methodology that ML uses to develop these models and ask, can that be applied to other modalities and other types of domains? Apply that same methodology to scientific data. That data could be text. I don't care. I mean, it could be text, but it could be any of our other range of modalities that scientists and engineers, you measure the stars. You don't get text. You get images in real and Fourier space, or whatever, but you could also use text. It could be simulation, gobs and gobs of simulation. It could be experiment, a satellite looking down rather than up, and you get all the measurements of every tree on the Earth. In court, spatial temporal inductive biases. Fine-grained understanding of spatial temporal is a big sort of missing point. I mean, computer vision does it in a very coarse way, but heavily engineered to certain use cases, but much more broader, incorporate time. So think if you do numerical PDEs, people spend their whole lives worrying about how to couple space and time for this particular PDE, right? So a lot of work to be done there. And so really want to develop these foundations. And the methodology of ML, in this case, is scale data size, model size, and compute so none of them saturate. And then do transfer learning. And that's very different than the way things are usually done. The way things are usually done in computational science is you take a big box, you simulate it to death. You run it until a deadline, until production, until your DOE credits run out. You just run it forever, and then you stop. Because you're giving the data as an input. So what we're doing here is scaling model and data and compute. So it's a trivial way to scale data. Just give it some trivially reproduced data or something. So the point is you need to have sort of a way to get more data such that if you get 10x more data, it's 10x different. So scraping the web's an obvious way, but can you do analogous things in other areas? So you get 10x more data, it's a little bit different. It doesn't need to be 10x different, it could be 2x different. 10x more data, 2x different. 10x more data, you do that, you get a scaling. So scale model and data and compute, so none of them saturate. And you get a model, because they haven't saturated, it's flexible, that you can then transfer learn. If you over-optimize and saturate something, it's not going to be flexible in the same way. All right, so we did this. We asked the question, could you do something like that? For a moment, I'm not going to talk about the scaling aspect. I'm going to talk about the transfer aspect, because it's easier to do as a hello world than scale up $100 million worth of compute. So I'll talk about the transfer aspect. Towards the end, I'll talk about some implementations about the scaling and how this may be different, the scientific sort of use cases than non-scientific. So a usual MO is to create pre-trained data, a bunch of data inputs. We'll talk about operators, neural operators, and Fourier operators if you're familiar with these things. They don't need to be this, but we're learning a function mapping, and operators of function mapping. So there's a lot of interest here. The general thing I'll be talking about will apply to neural ODEs and to pins as a way to regularize something, but a range of other things. So there's nothing special about that, but I'll talk about that here. And so what we really want to do here is to say, can we get a wide range of inputs, analogous to scraping the web lots of different ways, build up some sort of base model, and then transfer learn from it. So I want to learn on a physical system, and then I want to transfer to something else. So I want to learn when the viscosity of my PDE is between, train when it's 1 to 2, learn when it's 3 to 4, for example, right? Learn in a different thing. And you might say, geez, that's out of domain. How could I do that? And so you build stuff up, and if it's the case that I can take language models scraped from the web and do state-of-the-art time series forecasting on stock prices or whatever, you say, what does stuff scraped on the web have to do with ticks in the order book? If it has anything to do with it, it should be plausible that if I work on PDE type A, I may be able to transfer it to PDE type B. And we'll see that in some toy cases, but that's the way you should think about it. All right, so hello world, train on a bunch of different PDE systems, FNOs as a baseline. The general strategy, pre-train, we're not going to do quite the scaling, but pre-train in a way that's forward compatible with scanning on a, quote, large data set. Fine-tune, transfer learn on a downstream task and compare, all right? And you got to control a lot of things. So, Poisson equation. If you're familiar with it, here it is. If you're not familiar with it, here it is. Inputs. There's a diffusion tensor. So we're giving as input. I mean, oftentimes the way PDEs are formulated is on page 1, it says, assume that a solution exists and is unique, and then run from there. So what you've done is said, assume that something's saturated, and run from there. So really, day 1, nothing else is, so you should go back to page 1 on PDEs and say, I'm not going to formulate it in such a way, because in doing that, I'm saturating. So if you think of a PDE as a linear operator, so think of linear algebra, what you're saying is it's going to work with square matrices, because a solution exists and is unique. But I could be rectangular one way and do a more Penrose inverse. I could be rectangular the other way and do least squares. And it turns out being very rectangular in either way gives you a lot more flexibility in terms of parameters. So if my aspect ratio is 10x, I may be more flexible. I might need to find a minimum norm solution or a least squares solution. But if I get a low precision solution, not machine precision or 0 error, but 0.1 error, I haven't saturated. And by the way, I also scale my aspect ratio of my matrix and scale a bunch of other things. So you should think of it in a very different paradigm here. So input is diffusion tensor, forcing function. Outputs will be the solution to the PDE. Training data set is sample diffusion tensors and source functions in a reasonably broad way based on physical parameters that we can have some controls where we have numbers to say how far we go out of distribution. So a lot of machine learning is about saying how ignorant can I be and still solve your problem? How ignorant can I be about the specifics of your domain and still solve your problem, right?
A field, or is that a constant?
Well, it could be more generally. Here it's a matrix, it's a tensor. So it's a constant, but we may want to vary the aspect ratio in different directions and have some cross terms and so on. So yeah, and one way to measure out of distribution is the structure of that matrix, yeah. So you can do this for Poisson equation, but you can also do this for advection. And advection is some other equation. I don't know the difference between diffusions and advections. I mean, there's some terms there, but in both cases there's some field that I don't know the details of, but it happens to have some parameter that controls how nice it is, right? So apparently this tensor can also be a number or a matrix or a diagonal matrix or field or a lot of other things. And I want to say, jam it into, so you talk to my form factor. I'm scaling model and data and compute, and you generate your data that way. And with respect to that, these are the same. I mean, the niceness parameters might be more or less nice or more or less not nice, but do it the same way. Similarly, Helmholtz. It's going to have Way's number, forcing function, same thing. Talk to my form factor, I'll generate things. And so let's look at 3 different PDs. And these are nice because they stress test a range of different things, right? Hyperbolic ones are a lot less nice in certain ways. And so we looked at all 3, actually. So generate data with a range of different localizations and smoothnesses and a range of different things. And I'm going to have system 1 or 2 or 3. And I might want to train on viscosity parameter 1 to 2 and test on 1 to 2. Or train on 1 to 2 and test on 1 to 1/2, 1 to 1.5, or 1 to 3. And so look at a range of things there. And so increasing diffusion eigenvalue. So if I have a way to control the complexity of the physical structure, in a coarse way, I don't need machine precision, I just want 0.1 precision, I can do that with diffusion or advection diffusion or Helmholtz. And so we'll do it with respect to each of these. And you see the structures are different, but that's the form factor we want to talk to. Pre-train on some large, quote, large number of examples. Downstream tasks, MSE, log loss. I mean, some of that's we know the answers to, some of that's work in progress. Look at a bunch of downstream data sets and adapt. Do transfer learning to something new. Same physics, but systematically larger deviations in these physical parameters. And the adaptation could be zero shot or fine shot. And there's a bunch of details in the architecture. You got to normalize things properly. People always report number of parameters, but you got to control the embedding dimension just the right way. And there's, I think, a lot of work to be done there. OK, so this is the plot. Top left is what you want to look at. So what we're looking at is where we trained in blue, and I can't quite see the numbers. I think it's 1 to 3 here. And then where we tested, which is 1 to 5. Could be 1 to 3. We could have tested on 1 to 2. In the top left, we tested on 1 to 5. And so we trained a model and took that as a given. It's the road, it's the airport, it's given. I'm allowed to take that as a prior. You can't count that against my budget, right? That's the company credit card, so you can't count that against me. And as a function of new data, now I have a new experiment. I go out the world, I measure a few things. As a function of that, how well do I do? If I take that prior, that infrastructure you gave me, or if I start from scratch and train a new model, which is, again, a different way to frame a question than it's typical. Usually, a few years ago, if I tried to do this, people would accuse me of cheating. And what you see is when you train on 1 to 2 and test on 1 to 5, as a function of the number of examples, these are log scales, 2, 4, 8, 16, 32, whatever, I do well. It's 10 to the minus 3 in whatever units, right? And so I do about the same. Because I've trained here and I've tested on a superset of that. If I train the model from scratch and I have only 2 examples, I'm orders of magnitude worse, 4, 8, 16. And if I have 1,000 examples, I do about the same. But then I'm basically retraining something from scratch, right? All right, so this is if I train here and I test on a superset of that. What if I train on, again, I don't know the numbers, train on 1 to 3 and test on 2 to 4? A little bit out of distribution. Well, I don't actually be flat. I'm not actually flat here. I actually do improve. My model does improve as I see more examples. So as I see new examples from the domain, take the prior. It's a good, not great prior. New examples come in. I actually do a little bit better, not hugely better, but factor of 2 better, factor of 3 better. And of course, if I just take an untrained model, I'm orders of magnitude worse, and they level off. Now I train on 1 to 3, and I test on 1 to 3, 3 to 5. A little bit worse still, but get gradually better. If I start from scratch, worse, but get gradually better. And at the largest scale, they're the same. And if I train on 1 to 2 and I test on 5 to 10, so interestingly, I actually don't do so well when I start out, but I get a nice scaling law, linear on a log-log scale here. And I get a nice scaling law, and I'm quantitatively better, not qualitatively, but quantitatively better when I use the prior model. All right. So that was for diffusion. Same thing with advection, right? Because I don't know the difference. You just gave me parameters in the right form factor, and I trained here. So same thing with advection. The details are different. The y-axes are different. But the general shapes are similar. So what we see, and you see that for a bunch of other models also. I took, quote, the right size of the various layers in that thing. If you look in and say, what about if you vary this layer and that layer in different sizes? If the internal size is 64 versus a million versus 16 million versus 200 million, something levels off, the yellow levels off pretty quickly. So you're better, but at level. This is where you go and train on 1 to 5, test on 5 to 10. So, it levels off. Not so great. So you're really saturating the model capacity almost. But if you make the model much larger, both can increase, and they both do well when you have 32,000 examples, but in a wide range from 0 to 0 shot up to 8 or 16,000 examples, your orders of magnitude better. So the general technique of doing this transfer learning works. There's a lot of details and something. This appeared in NeurIPS about three months ago. And this was sort of Shashank Subramanian and Amir Gulami drove this bus, and so they did a great job. Some of you are probably familiar with this. And this is with, these are the LBL people working on ForecastNet originally. They're at NERSC. And so that was not large-scale compute, but we were having a pipeline to feed that into some large-scale stuff that I'm not going to have a chance to talk about today. So lots of open problems, go beyond simulation to do real experiments. Even this was toy simulation data, so get a broad range of more realistic 3D space-time, high resolution, et cetera. There's a big sim-to-real question that I think is a big opportunity in particular for places that have lots of experimental data and lots of compute. Train on lots of simulated data and then ask for a delta between the simulation to the real. And so that's something I'm not going to go into too much today, but there's a big opportunity there, I think. The architecture, we just took one architecture. There's a lot of work to be done there. And we know that that architecture doesn't scale. The particular scaling I showed you there was a little disingenuous. It's not the, quote, neural scaling. I mean, it's something that's forward compatible with that, but it's a very baby version of it. This wasn't big enough to really stress test that. We know that that doesn't, if you work on large-scale realistic climate models or something, they all do well on level off. And so you can say, my method's better than yours because I'm a little bit lower on the y-axis, but none of them scale. So in the sense of ML scaling, neural scaling, they can all go to HPC, but in the sense of the scaling you need for the foundation models. Self-supervision, a lot of other things. Mention the self-supervision because we have something up. Data-efficient operator learning via unsupervised pre-training. So something that NLP people do is take large documents and sort of construct semi-supervised tasks from that, and so predict next word or something. So do it in an unsupervised way and in context way. So, all right. So can we hope to train a foundation model? So I think the answer is yes. I think, now in the air, maybe these results aren't so surprising. It was good that someone did it. I think if you had this a couple of years ago, people would have been surprised and say, how can you learn different viscosities? So clearly, if you're learning something below a transition, a Mach transition, or when a nonlinearity kicks in, and so a wave front becomes discontinuous. I'll have a little more to say about that later, but clearly, there's going to be subtleties, and it's going to get more complex. So this isn't just saying it's all solved, but this is saying there's a reasonable path, and it's not insane to say, could you do it in very controlled ways for realistic scientific problems? And notice what I did. I said there's a viscosity parameter. I don't care what the physical thing is. I mean, my background's in physics, I happen to know, but how ignorant can I be and solve your problem? Right? So there's a viscosity parameter. Give it to me in this shape. And one of the big questions was, what if my objectives are misspecified or not? I mean, every objective in ML is misspecified. So I don't know or care what your viscosity parameter is doing. I want you to give it to me in a certain way. And it can't be dumb objectives, but the better you give me, the better I can map this onto. So that's sort of what we did. All right, so would incorporating physical knowledge help? It's not obvious it would, actually. Because if you don't do it very carefully, you may give yourself lots of flexibility, and that'll mess something up. You may just do it the wrong way. A lot of people have intuitions. I mean, a lot of big physical things, it may not be the pain point to getting something better. A lot of big physical systems, there's a box size, but the parameters really depend on the box size. And if you double the box size, you need to go back to scratch. And so, will it help? So the answer will be it can, and it has in very nice cases. When you stress test those cases, it often breaks. And it breaks for interesting reasons. So I'll give you some examples of that. And again, it's just the Euler method. The Euler method works if your function's incredibly smooth and nice. Page 1 of your numerical analysis book, but page 2 and 3 says do something else, right? So it's exactly, it's exactly that. All right. So there was something called pins that was popular a couple years ago. And the first paper to appear in a machine learning venue, there's 50 or 100 papers in science venues. The first paper to appear in a machine learning venue is ours. And we pointed out, characterizing failure modes here. So this has gotten 500 citations or something like that in 3 years. And in my experience, there's two groups of people who, and they react to this in two different ways. There's some people who think this is a terrible paper and it's awful and it's not fair because pins are good and you can fix the problems we identified. And there's other people who say, pins are bad and they have lots of problems and it's nice you pointed that out because no one else could. So I think both of those sort of miss the point that this is not about pins. This is really about the mapping between machine learning methodologies and scientific methodologies. Pins is a hello world way to do it. It's the Euler method, right? But this is not a statement about pins. It's a statement about if you want to tack on a regularization, one way to incorporate domain knowledge is to do that. That'll work well in nice cases and it'll choke in not nice cases. If you want to do this with neural operators, you'll get similar failure points. If you want to do this with neural ODs, you'll get similar failure points. So sometimes you put out a result and you have to beat the bushes to get attention. Other times you put this out and CACM put up an article 6 months later. I feel like to get an article in a place like this, you need a positive title. So they have a positive title. The more interesting thing here, I think, is the subtitle. So there's a promise. So this is about risks and opportunities. So to get an article in CACM, you need to point out the opportunities. Neural networks learn to speed up simulations, but the subtitle says physics-informed machine learning, I can't quite read it, is gaining attention, but it has problems and issues. Okay, good, that's good to know. But it also says it has problems and issues training. I mean, who wants to train? I mean, some people want to discover science, right? So it's also framed in a way to look for positive results, which is what machine learners do. They train. Doing diagnostics is a very much second-class citizen. So it has training issues. But under the hood, the things that are causing the training issues are just fundamental structural results that'll manifest themselves in training, they'll manifest themselves in diagnostics, and they'll manifest themselves in lots of other ways. So I'll talk a little bit about that paper. But so physical laws. Some people think of physical laws as an extra source of data. Other people think of it as giving what's in machine learning called an inductive bias. So in computer vision, you do convolutions. Why? Because there's a 2D image, and if you convolve stuff in 2D, you smudge and it has problems in your boundaries, but there's a geometry there so you convolve. Natural language processing, you might do something autoregressive because you're predicting something next in the sentence. So you use domain information, but in a very weak way. You might what time is it? 30? We have 35 to 40? Oh, okay. All right, so physical laws is additional. So you want to cook this in as sort of an inductive bias. So let's do that. All right, so lots of methods for incorporating physics into learning. Method 1, difficult to train. It's not the Euler method. It's a heavier duty method. Method 2, method 3, very easy to implement. Basically, take your PDE operator, tack it in on as a regularizer, and press the ML button. Now, regularizers are nice convex balls in machine learning and statistics. They have a shape. Differential operators are not that. They have a non-trivial null space, it's complicated, et cetera. So it shouldn't be surprising that if you just tack that on, you're going to have problems. So the methods actually don't work so well, even for simple problems. And essentially the issue is that soft constrained pins, when you tack the regularization on in a soft way, what you're solving is not that as a constraint. The constraint is not a requirement, it's a suggestion. And if you squeeze hard on that and look at the structure of the Lagrange dual space, which is what the stochastic optimizers are doing, now you have a million dimensions, or if you have 100 parameters, a million minus 100 dimensions to hide lots of mistakes in the Lagrange dual space. So there's many moving parts. The relevant ML methodologies don't play particularly well with the scientific methods. And this is so the reasons for the failure modes are interesting and informative. So let's say I want to do advection, the exact solution, choose a certain set of parameters, this is what you get. So not even close. And I'm not stress testing this to be 3,000 to 30 million, this is 30. So a quality measure, error, the beta is the physical parameter. I don't know what beta is, by the way, it's just some physical parameter they gave me. And so as you vary beta, at some point you do fine, and then boom, you hit a wall and die. And if beta equals 10, actually, it's perfect. That looks sort of bad, but this scale is 100, factor of 100 less than these scales. So this area is very small, so you do perfect. But as you go from beta equals 10 to beta equals 30, you hit the wall and die. And so essentially the reason is that the training surface, the loss surface becomes very complex. So if you're familiar with PDEs, think of this as a dynamical system that's stiff with 2 different degrees of freedom that couple in different ways. Nothing special about advection. You could do that for anything else. And so machine learning has a range of techniques where there's some theoretical infrastructure. One of them is called curriculum learning. The idea is obvious. The point is you can graft this onto machine learning theory. And the idea of curriculum learning is show the easy things first and then the harder things second. So it's a little bit like annealing a temperature parameter in simulated annealing. And so if you have a parameter that defines the hardness, show the easy things first and the harder things second. If you do that, you tend to do better. So that's not to say this was a remarkable result. It was the obvious thing to do. But you do the obvious thing to do that respects ML methodologies, and you do better on the physical problem. All right. So I'm going to talk a little bit about foundations, and I'll skip the implementations and applications just to give you an idea of what are the foundational things we might want to pull out of what we've been talking about. So one way to address the failure mode, don't run a neural network once, run it 10 times. You could have a Gaussian process, you could do something else, but get a mean estimate and a variance estimate. And there could be an empirical estimate by running it 10 times, and then do something. If you run it 10 times, then as a function of physical space or physical time, what you'll see is that there's homoscedasticity or heteroscedasticity over the noise structure. So what that means is the noise is either uniform everywhere or it's bad at certain spots. And you can imagine it's bad at places where physically there's a hard constraint, or there's a discontinuity. So if you have wave traveling in a medium below the speed of sound in that medium, the wave's sort of smooth. At some point you hit a transition, boom, and it becomes sharp. So compute the mean and variance estimates, which could be empirical. Update a model. It's like a discrete version of a Radon-Nikodym derivative. Basically just do the obvious Bayesian update. With an oblique projection, where that oblique projection incorporates information about the heteroscedasticity structure. Good for nice things, good for sharp discontinuities, good for hard constraints and hard boundary conditions. So look at the generalized porous medium equation. It's a nonlinear equation, but it gives you a parameter that goes from easy to nice. When it's easy, it looks like this. When it's medium, it looks like this. When it's hard, it's a Stefan problem, it looks like this. Think of this as a wavefront. And in the prior art, basically at the hard point, you're always shifted very strongly, statistically significantly to the left of the shock position. You do the oblique projection the right way, and boom, you get the shock position on the nose. So this is basically like a bootstrapping. We get a bunch of estimates. So you don't get a point estimate, because if you get a point estimate, essentially you have a biased estimate. That's what ML does, right? Especially at extremes. You get a biased estimate at extremes. This says, do an oblique, get 10 of those, get a variance estimate. You have a bias, do a biased projection. So think that I get something nice, and most of the time there's a bad spot at a corner. People do refinement of grid points near there. This is sort of doing this indirectly. A bunch of other types of foundation you can ask. Do something continuous, something about uncertainty quantification, something about weights, and something about time series. So I'll just mention each of those and then wrap up. Let's say I take a time series and I train data at time scale 1. I press an ML button. How well do I do if the test data is at time scale 1/2? You'd hope that, maybe if I go to time scale 2 or 4, it gets worse. But if I go to 1/2 or 1/4, it shouldn't go to hell. It shouldn't be terrible, right? So y-axis is time scale, x-axis is goodness. You use the Euler method, and this feeds into a neural OD, so literally it's an Euler. Boom, it does well. Orders of magnitude better, but then you go to 1/2, 1/4, 1/8, it does terribly. You've learned the discretization. It's a great discrete model for time scale 1. You go to 1/2 or 1/4, so it has none of the inductive biases of physical or spatial continuity built in. Cook in a midpoint, in RK4, boom, it goes down and levels off. A numerical integrator goes down to 10 to the minus 16 and levels off. This thing goes down to 10 to the minus 3 and levels off. But it levels off at a discrete basal level of noise. You can use this as an a posteriori check on how smooth you're doing. So you're getting a model that's meaningfully continuous out of domain in the spatial or temporal continuity. All right, wrap up. If you're over-parameterized, the UQ structure is very different than if you're under-parameterized. So if you want to do uncertainty, and you're talking about scientific ML models, realize you're on thin ice. You can talk to me. Could I even ask falsifiable questions about these models? Can you frame the question so that if it's framed in terms of training and testing and hyperparameter knobs, the answer is no, because you're not going to give me all your data to reproduce if you're Google. So ask questions just about the weight matrices, chew on them in smart ways, and you can make strong predictions about model quality without ever seeing training or testing data. Time series. Time is very interesting because it's a one-dimensional axis and you get heavy-tailed correlations. It's a great way to stress extreme value statistics. So a bunch of implementations that I'm going to black box today. And I'll wrap up just with the applications to say there's a bunch of popular challenges, learning solutions to PDEs, but don't try and solve a well-established problem, because even if you do a better job at beating them, they won't accept it and they'll beat you up and say, I could do something else better. Figure out a different problem. And very downstream problems that are very practical are do extreme value prediction. A lot of people are interested in that ML methods should do well if you don't saturate. Look at multi-scale modeling. There's whole journals on this, but it's not handled particularly well. Look at high-frequency inverse scattering. So I think these are future challenges with real scientific problems that cut across domains where ML will do very well, not if you take it off the shelf and graft it onto scientific methodologies, but if you get into the weeds and understand these foundational questions more directly, these are the sort of challenges that scientific ML and foundational ML methods should actually do very, very well on.
Yeah, thank you very much, Mike. Yeah, very thought-provoking to start. You have questions? Please come up to the mic, or the students can pass on the mic. Right, so were you using convolutions in any of your models?
Yeah, some of them had convolutions.
And did that matter as much?
Did it matter as much?
Did it matter?
What do you mean, did it matter? So a lot of them had convolutions. I mean, it's possible you could do some of these things without convolutions, so we didn't stress test that. If you do convolutions, I mean, just as an example, if your box is 3 by 1 and your convolutions are 1 by 1 or 2 by 2, you tend to do less well than if the convolutions are 1 by 3 or 2 by 6. So So the details, in a bunch of cases, like with vision transformers, you can remove them and implicitly do them in other ways. But if you're going to condition on using them, the details of the aspect ratio, the convolution stuff will matter a lot, if that's what you're asking.
Any other questions? You had so many things that we could chew on, but
oh, that's good.
Yeah. So
this is the key idea. The rest. So if you work on small things and you say my stuff will work on big things, that's much less compelling than if you have a whole bunch of slides at implementations at scale that you don't get to, because then people will believe you can scale it up. So we can scale it up, but yeah.
Yeah, I put you first.
But these are the key ideas.
I put you first by design because, I mentioned this twice yesterday. PDEs are probably the last place these things will work well, if they work at all. So I think you raised good, important questions.
And I don't think they need to work, I don't think they need to beat what PD people do. They just need to be better than bad, and then you can graft lots of stuff onto them. Yeah. So they need to be 0.1 or 0.01 good, not 10 to the minus 16 good.
Yeah. There is also this argument that if you take climate, you can train on reanalysis data, right, which PDEs are not meant for, so at least directly. So the last question I have is, any thoughts on how we can map across geometries in a non-parametric way? Because when we talk about operators, they operate on different geometries and different domains.
Going between dimensions, a lot of the language models, but a lot of the structure of transformers, depends on tokens. And so the Chronos thing I mentioned basically tokenizes, takes the language of tokenization and basically says, can you learn a mapping from that to a continuous time? So you've imposed the geometry in that learning of the discrete token. The discrete tokens have something. Adjectives go before or after adverbs, depending on the language, but you learn that mapping. So you can do that for 1D. For 2D, you can steal ideas from computer vision and do them a little bit differently. The interesting thing is going to be going to 3D with the tokenization, because there you get a big computational blow-up, and can you do it in sort of a finer grained way, I think. So I think going between dimensions is not trivial. If you take a single dimension, a single two-dimensional thing, and you say, I want to do tokenizations better or worse, and how do I handle geometry? That's something these ML methods should do well on. If I have a square box and I have a square box in a corner with it, and a smart ML method can't handle that, you should go home and cry, because this is what they're designed for. If you start the problem up and saying, I demand a well-posed PD, the solutions exist and unique, no, it probably won't. But if you say I'm willing to live with something that's over-parameterized or under-parameterized and use that extra dimension and data or features as an algorithmic source, then yes, definitely. Then you can fine-tune it to the coarse geometry again.
Waiting for a while. Very quick question, very short answer, and then we switch.
Professor, great talk. So I'm particularly interested in the scaling and the transfer behavior that you mentioned in your paper. So to test it on FNO model architecture. So I wonder if the scaling and the transferring behavior is model dependent. So what if you switch to maybe like vision transformer, any other type of architecture? Since they are maybe have different physics priors incorporating the models, so how does that perform?
Yeah, there's nothing special we did with respect to FNOs. We just did that because everyone likes it. I didn't want to argue about what operator we're using, but we have results, and the general what we talked about here would generalize to other sorts of mechanisms. So certainly that's the case. So when you talk about scaling, none of these models, none of these models scale in the sense of the neural scaling I was talking about. So it's not the case that we know how to change the structure of the transformer with respect to the neural Fourier or anything else. There's some people that are reported results that start to look like this, but they don't scale in the sense of neural scaling models. Or honest to goodness, you scale model and data and compute. And you say, here's the mechanism by which I add 10x more data, and I have a robust way to vary the number of heads or something in the architecture so that I don't saturate there. So none of them scale on climate and not toy stuff, on real stuff.
Catch him over the break. But thank you very much, Mike. This was really nice. Thank you.